Software engineering has shifted from manual syntax production to the specific discipline of defining constraints for AI agents. Hand a stochastic model an open-ended prompt at scale, and the structure quickly collapses. Agents force push to the main branch, commit sensitive .env files to public repositories, and saturate their context windows until the output degrades into hallucinations. The architectural solution to these failures is the Claude Code production playbook. We divide the deployment into 3 clusters: production workflows, advanced patterns, and sovereign fallback. Of 50 CLI commands, your daily workflow requires exactly 10. Specifically, commands for context hygiene, like /compact, and system diagnostics via /doctor. Mastering this playbook transforms AI from a volatile chat assistant into a deterministic, multi-agent engineering workflow. To force a stochastic model into predictable enterprise execution, you must implement the 5 pillars of vibe coding. Pillar 1 is constraint-first design. Before a single file is written, you generate a strict claude.md file to establish non-negotiable rules for the project's architecture and testing requirements. Pillar 2 is progressive disclosure. You restrict context bloating by using tight 100-token skill descriptions that act as precise trigger words. Only when the agent detects the exact domain requirements does the closed gate open, fetching the heavy reference payload into the context window. Pillar 3 is deterministic rails. Relying entirely on prompt engineering fails under enterprise load. The technical implementation for these rails requires pre-tool use bash hooks. These act as impassable gates that physically block unauthorized operations, like an agent attempting a git force push. Pillar 4 is context hygiene. You must flush the context at task boundaries and use the compact command to summarize history, preventing model degradation. Pillar 5 is sovereign fallback. You map local Ollama instances to your workspace, guaranteeing continuity during Anthropic API rate limits or when handling highly restricted data. These 5 pillars do not function as optional guidelines. They are the strict structural architecture required for safe, autonomous code generation. We can stress test these established constraints by scaffolding a React 19 application. We initialize our Claude.md with rules specifically tailored for this React environment, mandating ZOD-validated environment variables, zoostand state management, and co-located tests. During execution, our React component author skill recognizes the prompt trigger, loads into the context window, and initiates the Vite scaffold. To protect the primary context window from pollution during this build, we implement Pillar 4 by offloading research to a subagent. We deploy a read-only Haiku Explore agent and task it with scanning the local node modules directory for zoostand persist middleware options. The Haiku agent isolates its file scanning and returns only the requested summary data, keeping the main Opus or Sonnet context entirely unpolluted. Before committing the final code, we deploy a specialized Opus code reviewer subagent to read the diff and flag any accessibility edge cases. The result is rapid, automated construction. This high-speed execution succeeded specifically because the constraints preemptively blocked the AI from making architectural errors. Deep domain constraints function similarly in production, which we validate by building a Shopify section. Our Shopify section author skill enforces defensive liquid filters and wraps JavaScript in immediately invoked function expressions to prevent global scope pollution. We then create a closed-loop validation cycle with a post-tool use hook, physically forcing a Shopify theme check to run and pass after every single file write. Moving beyond single-agent coding validation, production pipelines eventually require multi-agent orchestration. Execution scales across 4 canonical workflow patterns: research plus implement, implement plus review, parallel feature builds, and sequential spec build QA. The parallel features pattern contains a critical vulnerability. When multiple agents share a single working directory and attempt to write code simultaneously, you get catastrophic file conflicts. The mandatory architectural solution is isolation worktrees. This absolute isolation allows 15 synthetic employees to operate concurrently on the exact same codebase, pushing independent commits without collision. Enterprise-scale production requires managing LLM agents as concurrent compute nodes integrated directly into Git infrastructure. Even with perfect Git isolation, enterprise-scale AI fails rapidly without strict token economics and sovereign cost orchestration. We enforce primary model routing logic by defaulting to Sonnet 4.6 for all standard feature coding and multi-file edits. We strictly limit escalation routing, reserving the expensive Opus 4.6 exclusively for complex architectural design and hard debugging. For offload routing, any heavy research requiring the agent to scan more than 10 files is pushed to the cheaper, faster Haiku 4.5 model. This chart maps out the dynamic cost matrix, routing incoming tasks into the optimal pipeline to stretch the token budget exponentially further. The ultimate fail-safe is sovereign fallback. We route routine implementation and restricted data entirely off the API to local, zero-cost Ollama models. Sovereign fallback is a strict architectural requirement that ensures 100% development uptime, regardless of API limits or network outages. This image represents the final architecture, a comprehensive pipeline mapping your CLI commands, Git hooks, multi-agent workflows, and token economics. We have successfully replaced stochastic, unpredictable prompting with deterministic system bounds. By writing the rules before the code, we lock the AI into a predictable groove where it executes flawlessly at high speed. Engineering massive enterprise systems now depends entirely on the architectural constraints you define.